Number 1, a Gallup poll conducted July 10th to the 14th in 2013 asked a random sample of U.S. adults, how much attention do you pay to the nutritional information that is printed on the restaurant menus or posted in restaurants, including calories and sugar and fat content? The sample results were that 43% of respondents said they pay a fair amount or a great deal of attention. Suppose there have been 500 people in the study. So, notice right now that they gave us a p-hat. They gave us a p-hat of 43%. They said 43% of the respondents said they pay a fair amount or a great deal of 500 people. So, the following graph displays the results from 1,000 random samples, each with sample size 500, from a very large population where 50% of the respondents pay some attention and 50% pay little or no attention. So, we ran this simulation here. We assumed a 50-50 split. We assumed our true population proportion was 50%. We're wondering, is it actually 50%? Is it? So we assumed it was 50%. We're wondering, did we actually get a p-hat of 43% if the true parent population, if the parent population, that population parameter was 50%? So can I really get a sample proportion of 43% if the population proportion is 50%? So to understand this sampling distribution, we need to know that there are 1,000 dots in this dot plot because we did it 1,000 times. And each dot in that dot plot represents what? Each dot represents a p-hat, a sample proportion. A p-hat, remember, is a sample proportion from a random sample of size 500, of sample size 500. Assuming the population proportion was 0.5. Assuming the true population parameter, the true population proportion was 50%. We're wondering, could I really get a p-hat of 43 if the parent population proportion was 50%? So that's what each dot in this simulation represents. There's 1,000 dots in that simulation, and we see that it's centered around 50%. We see the center of that distribution, that balancing point, is 50% because we assumed it was. We assumed the true population proportion was 50%. And we did that 1,000 times. We took a sample of 500 and found a p-hat. So, based on the simulation results above, are the sample data, our p-hat of 43%, consistent with the simulation? So, let's find our 43%. Let's say it's there for the sake of this example. For the sake of this example, let's say that's our cutoff for 43%. Well, what's the probability that our p-hat is less than or equal to 0.43? Based on this simulation, there's 3 dots, 3 out of, well, we did that 1,000 times. So that's 3 thousandths, which is approximately 0.3%. So the probability, what does this mean? The probability of getting a p-hat of 0.43 from a sample of 500, from a sample of 500 people with the true population proportion being 50% is 0.3%. So, is this consistent with the simulation? No, there's no way this is consistent. There's only a 0.3% chance that we get a sample with a p-hat of 0.43 or less. So no, it is not consistent with the simulation. Do these results cause you to question whether the population is really a 50-50 split on this issue? The answer is yes, it does. Yes. There is evidence that P our true population parameter is less than 50%. There's evidence that our true population parameter is less than 50% based on this population because we got a p-hat of 0.43, and this simulation shows that that p-hat of 0.43 probably did not come from a true a population that is p equals 0.5. Describe the effect on the mean and standard deviation of the sampling distribution if the sample size increased from 500 to 1,000. So as we increase sample size, the mean won't change. The mean will not change. It will still be close to the population mean, or the population mean. But the standard deviation will decrease. As I increase sample size, the variation in my p-hats and my x-bars will get smaller, so my standard deviation will decrease. So as we increase our sample size, the mean won't change. It'll still be centered around the true population mean or proportion, but the standard deviation will decrease.